Today I will be talking on the low radio frequency observations of nearby galaxies. So the question is why to make such studies? One of the main reasons is that most of the nearby galaxies below 1 gigahertz have not been studied yet. So many of their properties, which we know from higher frequency observations, I mean that above 1 gigahertz or so, tells us many of the interesting characteristics they have and their shape and so on, how they differ between, say, infrared and radio and how their correlation is. But on the other hand, at low frequencies, there are few advantages, and those advantages I list here. That what are the usefulness here? So one of the thing is that the mechanisms of propagation of cosmic ray electrons in spirals are not. So what I was saying is that the reason for studying things at low radio frequencies, these are some of the cases which I list here in the introduction. So one thing is that the mechanisms of how the cosmic ray electrons propagate in spirals are not really established till now. At meter wavelengths, what happens is that, as we know, that the synchrotron lifetime increases, and meaning it essentially goes as a root over of frequency, meaning 1 by root over of frequency. That means if you reduce the observing frequency by a factor of 4, the lifetime of synchrotron electron would go up by a factor of 2. And then what happens is that at lower radio frequencies, that's why that CREs can propagate to a few kpcs from their origin. Also, CREs are believed to propagate in general through diffusion, stripping instability, and advection. Now the issue is, when I say that they are not established, these are all believed, but it has not really been shown in that way, that okay, this is responsible, what is responsible. Now these are all done, meaning someone's in a paper putting it. What happens is that there are different models. You assume that model and then try to fit it. Now often what happens is that observed propagation scale could be explained by a combination of these, and there is no unique mechanism as of now we know, meaning we have been able to establish. So this is one of the main science cases of why study the cosmic ray electron propagation at lower radio frequencies particularly, because then what happens is that you can combine low and high radio frequency of low and high radio frequency studies to identify the propagation mechanism. So the combination of low and high radio. Okay. The next thing is, other than cosmic ray electron propagation, is that how the spectra of synchrotron electron changes with distance from the center of a galaxy or with star formation rate. So this is something which tells us how the star forming region is responsible in producing cosmic ray electrons. The few other studies, few other things which can be done based on these observations are that the slope of spatially resolved radio FM correlation is flatter using 0.33 gigahertz radio data as compared to higher frequencies, let's say at 1.4 gigahertz radio. So these are some of the things we are going to see. Other than the above, there are a few more important things. The question one would ask, in these galaxies, nearby larger galaxies, mostly spirals, what is the distribution of magnetic field strength in these galaxies? Also, how magnetic fields and star formation rates are coupled in these galaxies at less than kpc scales, that is better than a kpc scale. Also, how magnetic field and gas are coupled in the above scales, at the above scales. So what we need? We need multi-wavelength observations to trace different components, observations with high resolution and high sensitivity, and then of course one has to estimate the physically relevant parameters, which are basically like thermal subtracted spectrum, radio FDR correlation, cosmic electron propagation scale, magnetic fields, gas density, transformation rate, surface density. So these are the various parameters which one would need to estimate from these images or from the maps made at multiple frequency, multiple radio bands to get the relevant parameters. So this is just the same thing but in a different way, that how the non-thermal emission is at different frequencies. As we can see that at lower radio frequencies, which is from Condor 1992 review paper, that at lower radio frequencies is really the synchrotron emission which predominates, particularly below 1 gigahertz or so. Now, what one is doing basically model the thermal emission using H alpha or 24 micron or a combination of them, and then subtract this thermal emission from the total radio emission from images. The resultant non-thermal emission, which stays, provides multiple things. You can, as I mentioned already, that you can study the propagation of cosmic ray particles. You can study non-thermal spectral index from multiple radio observations. You can find radio correlation. You can also find sky plane magnetic field through minimum energy condition. So what's the sample? So the sample is, meaning the largest or the full sample, what we have chosen is a Spitzer local volume sample, that is the LVL sample of 258 galaxies within 11 megaparsec. Now, for most of them, we have in infrared, mixed, UV, H alpha, and optical band data. For many of them also there are data from Herschel, also in radio from GLA, CO observations, and H1 line emission data. Now, of course, most of them are not well suited for GMRT in the sense that they need to be well resolved, that there should be many resolution elements across the galaxies, and they should be visible for more than 4 hours from GMRT, and their angular size should be such that they are not resolved out with an interferometer like GMRT, which means that their size scales should be more than a few arcminute, let's say, which we have chosen is like greater than 6 arcminute angular size and less than about 17 or 20 arcminute. And this is the angular scale we have chosen. And so this sorts out 46 out of 256 galaxies which could be observed with GMRT. Initially, we observed 7 galaxies, 2 phase-on spirals, 3 edge-on spirals, 1 interacting star and 1 irregular, as pilot observations using legacy GMRT, which was with 32 MHz bandwidth at 330 MHz. We also used archival VLA data at L band, which is from 1.4 GHz, or in some cases from 6 GHz. So these are the galaxy images which I am showing. Their resolution is like typically about 10 arcsecond. RMS noise varies between 60 to 200 microjansky per beam, except of course NG63627, which is the galaxy on the top middle, which has an RMS somewhat higher, 450 microjansky per beam. And you can see that they are well resolved, and they are basically images shown in two. The 24 micron image is shown in grayscale, and often you can see that the radio emission is seen more extended than what we have seen in 24 micron. That is from the Spitzer images of the galaxies in grayscale. These are the other 3 galaxies. So, for example, for 4490, you can see extended emission, meaning extended large-scale radio emission, much more than which is seen at in the 24 micron. And this galaxy is disturbed. You can see that there is some amount of things coming out. It is known to be an interacting galaxy, which is interacting with this one here. And this is, of course, the classic one, M51, NG5194 in the middle. The other one is 4826. So, how are the galaxy-centric variation of non-thermal spectrum? This is being shown here for the 7 galaxies. As you can see, that typically the spectral indexes are comparatively flat. Comparatively flat, I mean about minus 0.5 or so of that order to minus 0.5 to minus 0.6. In some cases, can go slightly flatter, but the main thing is that the spectral indices are comparatively flat at the galaxy centers, because more star-forming regions are there, and they are really being produced in this star-forming region, the cosmic electrons. So, as a spectral steepening due to loss of energy has not really taken place. But as you approach the edges of these galaxies, so the x-axis is showing the distance from the center in kpc. Like 2683 has gone up to 4 kpc, 3627 has gone up to about the 7 kpc, I think. 4096 has gone about 6 kpc up to that. 4449. So it has gone into several kpcs, and as we approach towards the edges of these galaxies, the acceleration has really stopped beyond some point, and what we are seeing is propagation, which causes them to lose energy even at lower frequencies. And so that's why the spectral indices has steepened, particularly at 1.4 gigahertz. The propagation scale is smaller than at 330 megahertz. So that's why the spectral index is steepening. And so this is an indication that there is energy loss which is happening towards the edges of galaxies as we approach. And for example, for 5194, you can see that it has reached from -0.5 to about -1.3. So a spectral index steepening of almost like 0.8. Now, let's consider their propagation. So the cosmic electrons, as I mentioned, move away from source either by diffusion or through streaming instability or through advection, which you can also call as galactic outflow. Now, velocity of propagation have different dependence on frequency. So, for example, diffusion, the propagation scale is really proportional to root tau because it's random walk, whereas for streaming instability, it is proportional to tau, whereas for advection, it is really it is really frequency independent. Now, what happens is, as I mentioned, that the diffusion as such is also, meaning the propagation scale, that is the synchrotron lifetime, also can be shown to be proportional to 1 by root nu. Okay, so if you do that and consider two different frequencies, then what will happen is that at lower frequency divided by higher frequency, the propagation scale will go proportional to nu1 divided by nu2 to the power 1/4 for diffusion, whereas it will be proportional to root over nu1 by nu2 for streaming instability, whereas for advection, it is really independent of frequency. So that way, we can really say that by studying the propagation scale at 2 or 3 different frequencies, we can, to a reasonable extent, indicate that what is best fitting the observations. So here, of course, the data means what has been done to estimate the propagation distance. We have assumed the possibility electrons to lose energy as in calorimeter model, which predicts the radio-wave slope to reach unity. Now, use different convolution sites. So what happens is that you take FIR maps at 70 micron, keep on convolving them with different Gaussians till slope of radio-wave correlation is unity. So that is what is being done, because then it is believed that it is really the propagation, which is a convolution, and the convolution kernel here we have assumed to be Gaussian, and there the Gaussian full width half maximum is shown here, as you can see for 2683. Like if you say 130 plus minus 24, whereas at 1.4 gigahertz it is only about 21 arc-second. So there is a significant difference, but there are still significant uncertainties also have to acknowledge. Like here at 1.4 gigahertz, which we are seeing 21 arc-second. Now at 6 gigahertz, we don't really see any change. Now, so that's why the full width half maximum ratio are like is more reliable when you go to a larger frequency step. So that is between 0.3 and 6 gigahertz. And there you find that the ratio for these first 4 galaxies are first 2 are about factor of 6, whereas 4096 is more than 1.6, we can say. For 4449, we can say it is about 1.4 plus minus 0.3. For others, we can derive it. But again, here going through the numbers, turning the numbers in this kind of a talk would be somewhat difficult. So let's go for interpretation. So the main thing is, okay, before I go for interpretation, I would show one more result, that is which I mentioned is the radio FIR correlation. And here really the issue is that spatially resolved radio FIR correlation We have seen a few cases earlier from Basu and the Roy 2012 that the radio FIR slope fluctuates when you use the radio data taken from 0.33 GHz as compared to 1.4 GHz. Here also, so we wanted to increase the sample size to, for example, more like meaning earlier we had this case for about 5 or 6 galaxies. We have really increased the sample size by 7 more galaxies here, and which we see that the similar trend continues. So you can see the top one is 0.33 versus 70 micron. The lower one is 1.4 gigahertz versus 70 micron, and this is for galaxy 683. The top right is 3627. Bottom left is 4096. Bottom right is 4490. This is just an example of the four galaxies. The ratio and so on, that is the fitting parameters, are shown below. But again, I won't go for numbers here. So let's do for both these interpretation, meaning how we look at this, the interpretation from the previous two things, that is the radio, that is the propagation, and the radio effect correlation, what we find. So the main thing is, as a model of simple isotopic diffusion of cosmology electrons, we find that the scenario can explain the frequency dependency for only 2 galaxies. That is, if we assume diffusion out of 7 galaxies, the results could really be explained for only 2 galaxies. Whereas if we invoke streaming instability, could however explain the results for the majority of the remaining ones. What I mean is that out of 7, 5 remains. Out of 5, 4 galaxies could be explained by streaming instability, whereas advection could explain it for 1 more galaxy, the remaining one. So these results are really consistent with our earlier findings of a lack of unique mechanism of cosmology electron propagation nearby galaxies. And this is typical, which we have seen in literature also for few other cases people have done, but that is not using the same technique. People have used just modeling through a different approach. That is more of a theoretical model. They find through simulation, and then they try to fit that to the data. And so what happens is that out of these 3 different mechanisms which are responsible, in different galaxies, different mechanisms seems to predominate. And there is no meaning, it is not that out of 3, one is mostly responsible for many of the nearby ones. So no, there is no unique. The other one is that the next thing I come is the radio FI correlation. So this here, the average exponent from 0.33 gigahertz data, that is the radio FIR slope. The slope, of course, is the estimated from log-log plot. So it is that's why it's called exponent. So this average exponent from this 0.33 gigahertz data for 6 of the 7 galaxies. Of course, one galaxy was highly anomalous. We have excluded that. So excluding that, it is basically 0.63 plus minus 0.06 and is significantly flatter than the exponent 0.78 plus minus 0.04 obtained using 1.4 gigahertz data. So this indicates the propagation to have reduced the correlation between FIR and 0.33 gigahertz radio. So it is so why is the correlation reducing at lower frequency? That is the main thing, that where the source is, we are seeing radio beyond that. So when you are considering the source and taking the ratio between FIR and radio, if FIR is coming from a region, whereas radio is carrying it beyond that, so this will of course lead to a lack of correlation, and that is what is being seen. But still, the correlation is significant at the 330 megahertz radio versus 70 micron. Other thing is the measurement of magnetic field, the minimum energy condition. So this is basically, again, this is Beckett-Klaus 2005. This is a modified the equipartition formula through which from radio using the non-thermal spectral index and that is and several other parameters, one could estimate the equipartition, and this is equipartition magnetic field. So this is what we have done. So the magnetic field maps and its galactocentric variation is shown here. So these are for 3 galaxies I'm just showing, not for all here. So what you are seeing is that the equipartition magnetic field maps of NDC 449048265194. So they are shown in color with non-thermal emission at 1.4 gigahertz in contour, but the color really showing on top the magnetic field values At the center, they are highest, like for this galaxy that is top left, that is 4490. It reaches about 40 microgauss, and towards the edges, that is the blue part, it is about 10 microgauss, whereas it is about 30 microgauss plus for galaxy that is 4826, and it reduces to about 20 microgauss or so. So this is the radial variation, radial distance, which is normalized along x-axis, and the magnetic field normalized along y-axis. So what you see that as we approach towards the edge of the galaxy, the magnetic field drops by a factor of 2. The other thing which I just want to mention in short is the other parameter which we did was to do that magnetic field and star formation rate coupling. So the newer study has shown that the gas turbulence amplifies the galactic magnetic field in short time scale, and semi-analytical model has shown that the magnetic field and star formation rate surface density is coupled as B is proportional to sigma to the power 1/3, and this is from Shelke and Beck's 13 and 16, and this is not difficult to show because B is proportional to root rho if under equipartition of gas energy density and magnetic field energy. And whereas you have also star formation rate surface density is related through gas density through Kenket-Smith's law. So if you put together, you would expect B is proportional to sigma to the power 1/3. Now this global correlation is also found in 20 spiral galaxies. Now in spatially resolved way, this has been done only for a dwarf galaxy, which is IC10 by Basu et al. 2017, but it has not been done for spiral galaxies. So we carried it out. So this is the plots of correlation between magnetic field and star formation rate surface density for a combined sample of 7 galaxies, which was done earlier, plus 5 galaxies which have taken from Basu and Roy's publication of 2012. So these 6 plus 1, these are the 7 galaxies from our pilot sample, and these are 5. Our data are taken from Basu and Roy 2012. And what we're seeing is that in this log of plot, that is the magnetic field along y-axis, log of magnetic field along y-axis, and log of star formation rate surface density along x-axis, that they are really reasonably correlated, highly correlated. And the red lines are showing the fit to the data, and black lines show the plus minus 1 sigma vertical scatter. So, and the star formation rate surface density estimates are from FUV plus 24 micron for our 7 sample galaxies, and from Basu and Roy it has been done using H alpha plus 24 micron. So what is the thing? So mean value of this power index here, we expected 1/3, we find it's 0.31 plus minus 0.06. Support the semi-analytical model of Shelker and Beck, which is B to the sigma to the power 1/3. Our result is in good agreement with the expectation of star formation driven amplification of magnetic field. So this paper has also got accepted. This is very recently. We want to also study the magnetic field and gas energy coupling. So this is shown here. So again, log of magnetic field versus log of gas density, you take index of 0.5, or it is low to be 0.5. So estimated gas density is rho for a sample of 7 galaxies from archival CO and H1 observations studied and correlation with B. You find B is proportional to rho gas to the power 0.4 plus minus 0.09. This is broadly consistent with models which typically predict, like earlier even Chandrasekhar had predicted this almost like 70 years back in 1950s, that B is proportional to rho gas to the power 0.5. So this was the case, but other than the 7 galaxies, 24 more galaxies have been observed with uGMRT. We are not really going into any details of it. Some of these galaxies have already been observed, meaning already been analyzed and so on. So typically we are seeing a factor of 2 improvement in noise, which we expected anyway, because of larger bandwidth from 32 megahertz to about 200 megahertz. So factor of 2.5 we may expect, but here we are seeing about a factor of 2.5 or so in some of the cases. And we are also seeing, like, for example, halo, like this is from Irwin's paper, and this is for one of these galaxies, and that is basically the in this 4631, and so you can see this is currently showing more larger halo at lower radio frequencies as compared to L band meaning 1.4. So with this, I will really finish. So we have basically made spatially resolved maps of 7 galaxies at 330 MHz using GMRT. The non-thermal spectral indexes between this and the 1.4 GHz tend to steepen from the galaxy centers towards their edges. Slope of radio correlation flattened at lower frequencies. CRE propagation tails are of the order of gigahertz. No unique mechanisms found. Magnetic field is strongest towards the center by a factor of 2 than the edges. And the star formation rate, surface density, and magnetic field are correlated with a coupling constant of 0.01 plus minus 0.0. So they are a magnetic and turbulent galaxy density appear to be in equipartition. Small scale turbulent even amplification of magnetic field. So yeah, with this I will finish.
Okay. Thanks, Lashish. Questions? Few questions we can have. Then Surabhi.
So this is Suraj here. You told that magnetic field that is a star formation during the correlate it like 0.3 or something. Is it a what kind of heating you have done? Because I saw the data is very much scattered. So I can see.
Yeah. Okay. So this was done. Okay, just a moment. Yeah. Okay. So these things were really done through this bisector method. Now, meaning this was Shobhik did that. These fittings were done by Shobhik, but this is done by the bisector method.
But
as far as it remember.
bisector.
Yeah.
Yeah.
Okay, thank you.
Long live India and France friendship.